Hi guys, a very good evening. Again, the strength is very less. I don't know what is wrong. Many exams are going on still, people. Is there any exam going on in your schools? You are having unit test 3. Okay. I don't know, but for the past 2-3 weeks, the strength is very less. I don't know what is the problem here. We have chapters to complete. Okay. Right, let me share my screen. Physical exam is day after tomorrow, so maybe everyone is studying for it. Okay. Okay, fine. Okay, fine. Let me just speak to Raga once, right, and then we'll start the class. Okay, give me 2 minutes. Okay, fine, guys. We'll start. Okay, and we'll not have a class for 2 hours. Maybe we'll have a class for 1 hour. Right, we'll finish by 6:10, 6:15. We'll finish the class. Okay, right. So since the strength is so less, but I cannot go without teaching because it's been so many times we have been doing the same thing. Right? Okay, let me share my screen. So we will start with equilibrium. Okay. Right. So if we don't, before even moving on to the chapter, right, before even moving on to see what we are going to study, right? So this English word equilibrium, right, what should come to your mind, right? What comes to your mind when we talk about this term equilibrium, right? So one thing should come to your mind, right? When I say some system or something is in equilibrium, right, so there is going to be no change, right? This is the one which is going to be, this is the phrase which should be coming to your mind, right? No change, right? So what is not changing, right? Any measurable parameter, right? Any measurable parameter, say for example, temperature, the amount of substance, anything for that matter, right? So when I say some system is in equilibrium, right? Nothing of that particular, nothing related to the particular system is going to change. Okay, right. Now, when I speak in terms of chemical reactions or say physical processes, right? For example, say I take a physical process, like say for boiling, for example, right? Let us take boiling, for example, right? So what is going to happen here? You will have some liquid, right? And then you will be heating it, right? And there'll be some amount of vapors. Is it not? Right? Now, assume that this is water. Okay, this was water. Now at 100 degrees Celsius, right? At 100 degrees Celsius, what is going to happen? What will happen is that this there is some amount of gas, right? And there is some amount of liquid, right? Now at 100 degrees Celsius, what will you see is the temperature is not going to change unless and until all the water has boiled up, right? Unless and until all the water has boiled up, is it not? Right? So what is going to happen is there is going to be some kind of equilibrium existing. There is going to be some kind of equilibrium existing between the gaseous phase and the liquid phase. In the sense that the amount of gas is not going, like if I assume that this is a closed container, it is a closed container. Okay, so the amount of gas is not going to change, and the amount of liquid at 100 degrees Celsius is not going to change, right? And the temperature obviously is not going to change, right? So we see that nothing is changing. So we can say there is going to be an equilibrium established between the gaseous phase and the liquid phase, right? Okay, now how do we represent it? Right, remember that the equilibrium symbol is like this, the reversible process. This is a reversible symbol, right, which can be used for equilibrium symbol also, right, which can be used as a equilibrium symbol also, right? So now when I say there are two things which are going to be in equilibrium, that is the liquid phase and the gaseous phase in equilibrium. How do we write this? Say H2O in gaseous phase is in equilibrium with H2O in liquid phase, right? Now same thing can happen for any kind of physical process, say for example melting, freezing, anything for that matter. You will be at that particular temperature, melting point or say freezing point, right? At those temperatures, what will you see is that some kind of equilibrium will be established. Now this is not much important to us. Okay, this is not much important to us because obviously we are going to study about chemical reactions, right? How can we say that some kind of equilibrium exists in a chemical reaction? Right, now what we have to understand is, right, when I say chemical reactions, right, they can be of two types. One are what are called as reversible chemical reactions. The other one are what are called as irreversible chemical reactions, just like how we studied in your thermodynamics. Okay, we have reversible processes and irreversible processes. Whatever you saw at that time, right, holds good here also. Whatever the thing which you have studied about reversible and irreversible processes, right? Whatever you have studied holds good for an irreversible and a reversible chemical reaction also, right? We studied that in case of reversible processes, for example, they are very, very, very slow processes. Same goes with their chemical reactions also. Reversible chemical reactions are going to be very slow reactions, right? And irreversible chemical reactions are very spontaneous. We can say fast, or we can say that they're going to be spontaneous. Is it not? Right? Okay. Now, if at all you want to recap, what exactly, like how do we, analyze, or say, if I have to give you an analogy for what exactly is a reversible and irreversible process, right? Say I have a stone like this, okay, and this side a person is pushing, and this side also a person is pushing, right? Now, this side the person is pushing with a force of 10 Newton, right? And this side the person is pushing with say 9.999 Newton, something like that, right? Now what do you see? What will you observe is that this stone will eventually move towards this side only, right? The direction of movement will be towards your right only, right? But it is going to move in this direction in a very, 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 very slow pace, is it not? Because you understand that the difference in the force, this is 10 Newton, this is almost 10 Newton, but little lesser than 10 Newton, right? So eventually it's going to move this side, but this stone is going to move in a very, 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 very slow pace, right? Now, These kind of processes are what are called as reversible processes. Now, why do we say it is reversible then? Right? When I say some process can be reversed, it is not about you will be able to you will be able to reverse it by whatever means possible. No, it's not like that. Right? We should be able to reverse the process with minimum amount of energy spent, or ideal cases, we should be able to reverse the process with almost no energy spent. Okay, without spending energy, or say without spending much energy, if you are able to reverse the process, those kind of processes are what are called as reversible processes. Right? Now in this case, it is very easy to make the stone move this side if very little amount of energy is spent by this person who is pushing here toward, and it will be able, and this stone will be able to move this side. So we'll be able to easily reverse the direction of this direction of motion for this particular stone with very minimal amount of energy spent, right? Okay, but in case of an irreversible process, say the irreversible process can be, say, here I have 10 Newton, here I have only 1 Newton, right? Now this, for obviously this stone is going to move towards this side only, but for this stone to move towards this side, this person has to spend a very huge amount of energy. Okay, this person has to spend a huge amount of energy. And what will understand, if it is 10 Newton here and 1 Newton here, this ball or this stone will move very fast, right? This stone or ball will move very fast, because here I have very high force, here I have very less force. Okay, now these kind of processes are what are called as irreversible processes. Okay, now the same thing can be applied for a chemical reaction also, people, right? Okay, fine. Now in case of equilibrium, when will I say that there is some equilibrium? Right, now I would say the moment you see that here I have 10 Newton, here I have 9.999 Newton, like the ball is moving towards this side and nothing is changing, is it not? Nothing is changing. Whatever the velocity with which the ball was moving, the same velocity only will be keeping on moving like that, right? The amount of stone doesn't change, the force doesn't change, nothing changes. So I would say this stone is actually in equilibrium. Okay, this stone is actually in equilibrium. Okay, right. So we understood that this is how a reversible process works. This is how an irreversible process works. Now, how are we going to, accommodate this in case of chemical reactions, right? How are we going to do that? Let us try to understand, right? Look at this, people. Say, when I have a chemical reaction, say I have A giving B, or say I'll write R giving B, reactants giving products as the reaction. So normal general reaction. Okay, right. Now what I'm going to do is that I am going to plot a graph between concentration and time. Okay, I am going to plot a graph between concentration and time. Okay, right. Now remember, whenever we write in brackets some species, right? In brackets some species, like the bracket of R, bracket of T, all these represents concentrations, right? So when I say bracket of R, means it is concentration of R. When I write bracket of T, it is concentration of T. Okay, right. Now what will happen? What do you think? Now we know that as the reaction progresses, right? As more and more time, say at time T is equal to 0, I start with an amount of reactant, say 1 mole of the reactant, right? Now what will happen? Eventually, as the reaction proceeds, that particular concentration of reactant will keep on decreasing. Right? I hope that makes sense, right? As the time proceeds, as the reaction proceeds, what is going to happen? The concentration of reactant decreases, is it not? Because more and more reactant is consumed during the reaction, right? And obviously the concentration of products, and the concentration of product keeps on increasing, because eventually, like initially you wouldn't have had any product, right? But as the reaction progresses, more and more amount of product gets formed, more and more amount of reactants gets consumed, and more amount of products gets formed, right? Now this you have to understand very carefully. As the time progresses, the concentration of reactant decreases, right? Or say the amount of reactant decreases, and the amount of product, or say the concentration of product, keeps on increasing, right? So if I have to plot this particular thing in the form of a graph, how will the graph look? We'll try to understand, right? So let us talk about the reactant first, right? Now initially at time T is equal to 0, this is the starting period of the time, right? When time T is equal to 0, we will have some amount of reactant here. Is it not? We will have some amount of reactant here. Say we will call that as initial concentration Ri. Okay, this is your initial concentration of the reactant, and that is represented by Ri. Okay, right. Now what is going to happen? As the time progresses, say this is 1 minute, 2 minutes, 3 minutes, 4 minutes, 5 minutes, like that, the time keeps on changing. What will you see is that this concentration keeps on decreasing. Okay, this concentration will keep on decreasing. Okay, now, okay, fine. That is one thing, but we'll still talk about this graph later, a little more in detail. Okay, now, this is about the reactant part, right? The concentration of reactant keeps on decreasing because this is say 1 m, this is 0.5 m, this is 0.25 m, 0.125, something. It keeps on decreasing. Okay, right. Now, what happens to concentration of products, right? Now, if you look at the concentration of products, let me use say black color for that, right? Initially, say the product concentration would have been 0 because the reaction has not started, right? And the product formation didn't start yet. Means what? The concentration of product is 0. Now, initially, right, at time t is equal to 0, right, the concentration of product is 0. Right. Now, as the time progresses, as the reaction proceeds, what is going to happen? The amount of product keeps on increasing, right? The amount of product keeps on increasing. So you will find that the graph goes like this. Right. I'll draw it again. So you will see that the graph goes like this. Okay. Right. Now, till this point, if I talk about the reactant part, right? If I talk about the reactant part, till this particular time period, approximately, till this particular time period, okay, what do you see is that the concentration keeps on decreasing, right? The concentration keeps on decreasing, right? But after this time period, say after 3 minutes, right? After 3 minutes, what are you seeing? That the concentration of reactant is not changing at all. Whatever was the concentration of reactant here, right? Whatever was the concentration of reactant here, that particular concentration is not changing at all, right? Whatever was the concentration here at 3 minutes, right? That particular concentration is not changing at all. Okay, right. Now, what is happening to product? Again, you see approximately in the same time period, approximately only I'm telling, okay? Approximately at the same time period, if at all the graph is like this, okay? The graph is like this, right? Approximately at the same time period, what you're seeing, the concentration of product also is not changing. So whatever is the product concentration here, right? Whatever is the product concentration here, that concentration of product is not changing after a particular point of time, right? Now, why this happens, we will analyze it later, right? Why this happens, we'll analyze later. But people, now is the concept, now comes the concept of equilibrium to us. How? What did I say? We said for equilibrium to be established, the amount of reactant, the amount of product, or any other measurable parameter should not be changing. Is it not? Right? Any measurable parameter, be it concentration, temperature, whatever be the parameter you're talking about, right? That particular parameter should not be changing. Right? Now, what are you seeing? After this particular point of time, say 3 minutes, what are we seeing? We are seeing that the concentration of product as well as the concentration of reactant is not changing. Okay. So what will I tell is that at this particular time period, I will tell that equilibrium is established. Right? At this particular time period, but for the time period when the concentration of reactant, or say the time period after which the concentration of reactant and the concentration of product is not changing, that particular time period, I would say, is where the equilibrium is established for this chemical reaction, because the concentration of product as well as the concentration of reactant is not changing. Right? So we are going to concentrate on this part. We are going to concentrate on this particular parts where the concentration is not changing. Right? Now, this parts, that is when the concentration is changing, right? When the concentration is changing, right? Till this time period, the concentration is indeed changing, right? When you want to talk about these parts, we'll talk about this in 12th, right? In 12th, there's a chapter called as chemical kinetics, right? You will study before the equilibrium is reached. Before the equilibrium is reached, there are still the concentrations of reactants and products are changing, right? So at that time, we'll be interested in something called as chemical kinetics, the rate of the chemical reaction, right? How fast or how slow the chemical reaction happens. That we'll be able to deal with in our 12th class in chemical kinetics. But in 11th class, we are going to deal with after the equilibrium is established. After the equilibrium is established. Okay, right. Here also we'll be speaking about the rates. Okay, don't worry. Here also we'll be speaking about the rates, right? But not so in detail, but little wherever required, we'll be touching it. Here also it is required, okay, but not in so much detail. Okay, right. Now, second thing is this whatever we talked here, okay, whatever we are talking here is a case for a reversible chemical reaction, right? Is a case for a reversible chemical reaction. Why is it like this? Why is it like this? You guys understand. Or say from the graph, you will not be able to, expect much, right? But actually from the graph also, you will be able to understand. Okay, right, fine. So people, what happens here is that we will be representing reversible chemical reactions like this, as I told, right? Whenever you want to represent a reversible chemical reaction, this is how you represent a reversible chemical reaction. What do you understand by this? R will be able to form P, right? And the product can in turn form the reactant also. That is, reactant can form product or the product can form the reactant, depending on the conditions, right? Depending on the conditions. So both side reactions are possible, right? But the same thing, if you want to represent irreversible chemical reaction, that we represent normally R giving P like this. That means what? Only reactants are capable of giving products. Products are not capable of giving reactants. Okay, right. In our chapter equilibrium, okay, we are going to study only about reversible chemical reactions, and we are not going to talk about irreversible chemical reactions. Okay, we are not going to talk about irreversible chemical reaction. Now, why is it like this? Why are we not concentrating on irreversible chemical reactions? Right, that is very simple, right? See, now let us understand, right? Say for example, I have Na plus H2O giving NaOH plus H2. Okay, I have this reaction with me. Okay, now you understand, please understand that when I add NaOH plus H2, there is no way possible that you will be able to form sodium and H2O. I think you might have even done this reaction in 10th class if you have gone to your labs, right? If you have not gone to your labs, maybe whenever you go to your labs, ask your lab technician or your teacher to do this experiment, right? Take a small piece of sodium and put it in water. The reaction will be very violent reaction, right? The reaction will be very violent amount of reaction. Okay, right. So that means what? This is a very fast reaction, very fast reaction, very spontaneous reaction. The moment you drop a piece of sodium in water, right, it is going to react and very fast, and it is going to form NaOH and H2, right? But in the other case, say I have NaOH, I pass H2 gas into this, right? There is no chance that you will be able to form sodium and H2O. Okay, that is not possible at all. Okay, right. Now you can ask me, sir, that means in case of irreversible chemical reaction, there is no equilibrium? No, it's not like that. Okay, in irreversible or reversible chemical reaction, there is indeed equilibrium. Okay, because at some point of time, there is going to be this thing where that nothing changes, right? The concentration of reactant, the concentration of product, nothing changes. But the problem with irreversible chemical reactions is like this kind of chemical reaction. Say if I have started with some 10 grams of sodium and I put in some amount of water, right? So what is going to happen is this is a time t is equal to 0. Now say at some time period t, okay, I don't know, say 1 minute or 2 minutes or 3 minutes or whatever it is, this amount of sodium would have become 0. Okay, this amount of sodium would have become 0 grams. All the sodium would have actually gotten reacted. Okay, all the sodium would have actually gotten reacted. Okay, now only at this point, I can say that the equilibrium is reached, because after that nothing is going to change, obviously. Right, after that nothing will change, right? Because not what will change? Nothing is there to change. What will change, right? So that is the problem, right? So obviously equilibrium is reached, right? But if at all you want to study about the equilibrium, if at all you want to give some quantification, give some numbers, do some mathematics on this particular kind of processes, that is going to become very difficult, because you have some 0, because anything into 0 is 0, anything divided by 0 is 0, right? Anything plus 0 will give you the same value, right? Anything minus 0 is going to get the same value. So because of this 0, in case of any irreversible chemical reaction, in case of any irreversible chemical reaction, which are going to be very fast and spontaneous, right? At least one of the reactant concentration is indeed going to become 0. Okay, and that is going to create a lot of problem, right? That is why mathematically we will not be able to analyze your irreversible chemical reaction, right? Because we have understood that mathematics, whenever 0 appears, there's going to be a lot of problem, is it not? But in case of a reversible chemical reaction, you will see that this 0 will never even happen, right? This 0 will never even happen at all. Say if at all I want to represent that particular concentration versus time, right? For sodium, say for sodium, I started with 10 grams and this sodium would have actually gone to 0, right? Would have actually gone to 0. This is the amount of sodium, right? But you look at that graph, you look at this graph here, right? Where is the concentration of reactant? The concentration of reactant is here, right? And that is no way going to touch this axis. Never it will happen in case of a reversible chemical reaction. Okay, we will try to understand why also. Don't worry about that. We'll try to understand why. Okay, but in this case, whatever be the amount of sodium we took initially, that eventually is going to become 0, and that is the reason why we will not be able to mathematically analyze what is happening, mathematically analyze the equilibrium part of a irreversible or a fast or a spontaneous chemical reaction. Okay, I hope that makes a lot of sense, right? Okay, now let us try to understand what exactly will happen in case of irreversible. Now we study the irreversible, right? What will happen if I have a reversible chemical reaction? How are you going to analyze that, and why is it that something is not becoming 0? All those we will try to understand. Okay, right. So let us take some general chemical reaction, a reversible chemical reaction, R given P. Okay, right. So fine. Now, right, let us start with, say, at time t is equal to 0. At time t is equal to 0, that is initially, right, we had, say, some 10 moles of the reactant and 0 moles of product, obviously because the product formation didn't start yet. Okay, right. Say now after some t is equal to 5 minutes, right, after t is equal to 5 minutes, right, what I see is that out of this, let me write it a little down. Okay, so after some t is equal to 5 minutes, right, what I see is that out of this, say 2 moles reacted, right, 2 moles reacted. Okay, 2 moles reacted. Okay, so can I tell? So 2 moles has reacted already. How many moles will be remaining? 8 moles of reactant will be remaining. Okay, 8 moles of reactant will be remaining. Okay, so whatever has reacted here, right, in this case you can understand the stoichiometry also. 1 mole of reactant gives 1 mole of product. So 2 moles of reactant will give 2 moles of products. Okay, if 2 moles of reactants are reacting, that will give 2 moles of products, right? So here we would have gotten 2 moles of products, right? No issues. Okay, fine. Now after some another 5 minutes, say 10 minutes, what is happening is that we have only 8 moles left, right? Out of these 8 moles, now another 2 moles is reacting. Okay, another 2 moles is reacting. So overall, how much is left? Only 6 moles is left, right? So now already I had 2 moles. So another 2 moles will come. Totally now we have 4 moles of products. Okay, right. Now what is going to happen is, say after another 5 minutes, say 15 minutes, right? Now I have 6 moles, and out of this, say another 2 moles are reacting. So how much is left? 4 moles is left. Okay, some 4 moles is left, and I already had 4 moles here. Another 2 moles is going to come because 2 moles are reacting. Totally now I have 6 moles of products. Okay, right. Now if I check for another 5 minutes, say 20 minutes, what is going to happen is the reaction is going to get reversed. How is it going to reverse? Let us try to understand. Say now I have 6 moles of products, right? Okay, now I have 6 moles of products. Now what will happen is this 2 moles of some product will react to form. I already had 4 moles of reactant. 2 more moles will get added because 2 moles are getting reacted here to form reactant here, right? 2 moles of product react to form 2 moles of reactant, reversible process, right? Now how much I have? Basically, I'm going to have 6 moles, right? Now another 5 minutes, 25 minutes, what is going to happen? Another 2 moles will react from reactant side to go to the product side, right? Say another, if I had here only 4 moles, right? Now 4 plus 2 will become 6, and here I have 4, right? Again, what is going to happen? And another at 20, at 30 minutes, again 2 moles of this are going to react. Again, it is going to come back from this side to form 6 moles, and here it is going to be 4 moles. Okay, right. What are you seeing here? What are you seeing here? Now, till this point, right, the reaction was properly happening, right? Till 15 minutes, the reaction was properly happening, right? After this point, what are you seeing is that this 6 moles or 4 moles or 6 moles or 4 moles, that particular value is actually not changing at all. Whatever is the amount of reactant that is reacting and going to the product side, again I'm repeating, say here 2 moles of reactant are reacting, right? Okay, here, right? Or in this case, 2 moles of products are reacting, it is going back to the reactant side. Now that same 2 moles of reactant is reacting, it is going to the product side. Again, that 2 moles is again reacting to go back to the reactant side, right? So eventually what you are seeing, this number 6, 4, that is 6 moles of reactant and 4 moles of product is not changing at all, right? Whatever is the amount of reactant reacting and going to the product side, the same amount of reactant is reacting and going back to the product side. Sorry, again I repeat, whatever is the amount of reactant reacting and going to the product side, right, that same amount of product will react and go back to the reactant side. Is it not? Right? So even though you see that some kind of reaction is indeed happening, say back and forth, it is happening, right? But overall, if you check, overall change is indeed nothing. There is no change overall, even though you see that some kind of reaction is happening back and forth, right? So this kind of equilibrium is what is called as dynamic equilibrium, right? What do you mean by dynamic? Dynamic means something is moving, right? Something is moving, but still there is equilibrium because overall there is nothing changing. Okay, overall there is literally nothing changing, right? I hope that makes a lot of sense, right? So I would say at this point, equilibrium is attained, right? Because after this 6 and 4 or 4 and 6, whatever you want to take as the equilibrium concentration, that particular value is not changing after that particular point of time, right? Overall, the change is nothing, right? And as I told you, this concentration, that is the reactant concentration or the product concentration, will never, ever become zero, right? The reactant concentration or the product concentration will never ever become zero because it is going to be dynamic, right? After a point of time, even though the reactant is going to go to the product side, again the product will react and go back to the reactant side, right? So the reactant concentration can never become zero in case of a reversible chemical reaction. Okay, so that is the beauty of having a reversible chemical reaction. We can be mathematically analyzing it. Okay, it is very easy for us to go for mathematical analysis of a reversible chemical reaction, that equilibrium, right? But in case of irreversible chemical reaction, since some of the reactant concentration is becoming zero, we will not be able to mathematically analyzing it. But that does not mean that equilibrium is not attained. Equilibrium is attained at the end of the reaction. At some point when the concentration becomes zero, yes, I would say that at that point equilibrium is attained, right? But we will not be able to mathematically analyze it in case of an irreversible chemical reaction, but we will be able to do it very efficiently. What efficiently? Mathematical analysis of the equilibrium of the reversible chemical reaction can be done very smoothly, very efficiently. Because why? Because the concentrations are not becoming zero. Okay, the concentration of reactant as well as the product is not becoming zero. Okay, right. Now we can analyze one more case also, right? Now in this case, we started with 0 moles of product. There was no product indeed, is it not? There was no product at all initially, right? But it is possible for us to start with also some amount of product. That is also okay for us. That is possible only in the case of reversible reactions. Okay, right? So the graph also might change. This graph, whatever you saw here, what is there? At time t is equal to 0, you are finding that the product concentration is 0. Is it not? Because initially there was no product. Okay, but At time t is equal to 0, I can also have amount of product present, right? Say for example, I have this reaction N2 plus 3H2 giving 2 ammonia. Okay, now at time t is equal to 0, I can have 1 mole of this, 1 mole of this, 1 mole of this, and start the reaction. Okay, I can have 1 mole of this, 1 mole of this, and 1 mole of NH3 also in the same reaction mixture. All these are gases, right? Right, all these are gases. So I can have N2 gas, I can have H2 gas, I can have ammonia gas, and you can understand that either the forward reaction will happen or the backward reaction will happen. That we don't know. Okay, that we don't know for sure, right? Which side the reaction can happen, because that, but again, at the end of this particular chapter, right, when we finish this chapter, you will be able to predict, right, when we start with reactants as well as products, right, when we start with reactants as well as products, we will try to understand how to predict which side the reaction will happen, whether the forward reaction will happen or the backward reaction will happen. We will indeed be able to predict it, but not for now. Right? For now, we will assume that the reaction is going to move in the forward direction only. Okay, we will assume that the reaction is actually going to move in the forward direction only. Right? Okay, anyways, so if at all I plot a graph, right, if at all I plot a graph, the concentration of N2 and H2 will keep on decreasing, right? And the concentration of NH3 will keep on increasing. Is it not? Right? Say now we start, we'll use 3 different colors, right? Say for N2, we'll use this color, right? This is N2. Initially, I had 1 mole, okay? And that concentration keeps on changing, right? And say we use the same concentration of H2 is also there, and that concentration also keeps on decreasing, right? That concentration also keeps on decreasing. And say for NH3, initially I had 1 mole, whatever, right? Now that concentration keeps on increasing. Right? So like this, will be able to time graph. Now, what are you seeing? The product concentration is not starting at 0, but rather it is starting at some other value. That is also okay. That is what I'm trying to say. Okay, that is also okay to start with some amount of product initially. That is fine, right? And these kind of things are possible only in the case of reversible chemical reactions. Okay, right. So now we have understood the reaction, and we have understood reversible processes, irreversible processes, how equilibriums are established, everything we have understood quality wise, right? We have understood the concepts, right? Let us try to apply some mathematics to this. Okay, we will try to apply some mathematics to this particular thing which have already been seen, right? And as I said, we are going to deal. Oh, yes, any questions that you have? Yeah, I think you have to mute yourself.
Sorry, sir.
Yeah. Okay. Right. So what I was telling, now we'll apply some mathematics to this. Okay. Right. So now for us to apply some mathematics to this, okay, and before that, right, now we say that at this particular point, to be in this particular time period, after 15 minutes, we say that the equilibrium was attained. Isn't it not? We said that the equilibrium was attained, isn't it? Right. Now, if you see, there is one particular condition for equilibrium to be attained. For equilibrium to be attained, right? And what is that condition, if you ask me, right? There is one condition, or say only if this particular thing happens, then I would say that equilibrium is attained, right? What is that condition is, right, the rate of the forward reaction, should be equal to rate of the backward reaction. Right? Rate of the forward reaction should be equal to the rate of the backward reaction. Okay. Now, what am I trying to say here? Now look at this, people. right? See, for now, all that we have to understand is when I say rate, right? Like you might have known this, right? Whenever we talk about rate, it is something with respect to time period, right? It is something with respect to time period, is it not? Now, when I say rate in terms of a chemical reaction, please remember it is always equal to change in concentration, right? When I say delta, what is delta? Delta is change. Change in concentration by change in time. Okay, change in concentration divided by change in time. All right. Okay. Now we have to go into so much details of this, what exactly is happening here. But all that you have to understand is when I say rate, it is always change with respect to time. Some say when I, for example, velocity, right? When I say velocity, what is this? Velocity is rate of change of displacement. Right? That means what? When I say velocity, that is rate of change of displacement. So we'll write displacement divided by time. That is del t divided by del t. Change in displacement by change in time. Right? Here also, here we're telling rate of chemical reaction means rate of change of concentration. You can write it here. Right? This is nothing but rate of change of concentration. Right? That is what we have to understand. Okay, rate at which the concentration of reactant or the concentration of product is changing. Right? Now, if you understand this, like look at this, right? Say if I consider that if I consider this particular place, or maybe I'll consider these two time periods. At time t is equal to 20 minutes, 2 time t is equal to 5 minutes. Okay. Now let us check what is the rate with respect to the concentration of reactant. Right? We are talking about the rate with respect to concentration of the reactant. Okay. Now I told you that it is nothing but change in concentration by change in time. No issues. Okay. Now what is happening here? Between these two, right? The change in concentration, 4 is becoming 6. Is it not? 4 is becoming 6. So the change in concentration is 2. 6 minus 4 is 2. Okay, right? So the change in concentration is 2 because 4 is becoming 6. I'm talking about the change, not the exact value. We're talking about the change in concentration. That is nothing but 2. Right? Okay. Now what is the time period? Time period is 20 minutes to 25 minutes, means overall what is the change in time period? 5 minutes. Is it not? Right? Okay, that is your rate with respect to the reactant. Okay. Now when I check the rate with respect to product, what is happening? Let understand. Right? Now initially I had say 6 moles, right? And that is becoming 4 moles. Right? Or I would say initially I had 4 moles, it is becoming 6 moles. Whatever it is happening, the overall change between these two is 2 moles. Is it not? The overall change between these two is 2 moles. Is it not? Right? So obviously the change in concentration, that is R is equal to rate is equal to change in concentration by change in time. So the change in concentration of product is 2 moles, right? And what is happening to the time period? Again, from t is equal to 20 minutes to t is equal to 25 minutes, the change in time period is 5. Now what are you seeing? When the moment equilibrium is reached, right? The moment equilibrium is reached, what are we seeing? The rate of reactant is actually equal to the rate of product. That is why we say the rate at, or what is the rate of reaction? I mean, rate of reactant can also be written as rate of forward reaction. That means reactant giving product, right? And when I say rate of product means what? Rate of backward reaction. Rate of backward reaction, that means product is giving reactant back, right? And both these values are becoming equal, and that happens, then only we can say that the equilibrium is reached, right? Then only we can say that the equilibrium is reached. Okay, right? So keeping this in mind, that is a very important condition. For equilibrium to be attained, the rate of the forward reaction should be equal to the rate of the backward reaction. But in other cases, right? In other cases, what will you see? Say till that 15 minutes, right? You will see the rate at which the reactant forms reactant forms product, and the product forms reactant is not even happening. So eventually the rates are different, right? But the moment equilibrium is reached, what will you see is that the rate at which the reactant form products will be the same rate at which the product also forms the reactant. And that's why you see the overall rate is not changing at all. I mean, the overall change is not changing at all. That's why we say equilibrium is reached, right? So all these are connected. Okay, all these things are very much connected, right? Okay. Now, as I said, right, let us apply some mathematics to this. Let us try to understand what do you mean, or like some for this equilibrium process. Let us try to understand how do we apply, how can we apply some mathematics to this, right? So for this process, right, we will be able to, we have to know one law, and that is going to help us a lot, right? So that law is what is called as law of mass action. Okay, that law is what is called as law of mass action. Okay, right. Now you can take the statement for this. Or maybe you don't have to take this now, right? What happened? Some charts are coming. No issues, right? No issues. Right. So what we have to understand is like we maybe we'll see this in the next class. Okay, from law of mass action. We'll finish it for today because the strength is very less, right? And tomorrow, let me see if there are active students are going to come or not, or else we'll not have the class. Okay, right? So we'll finish the class for now. Okay, and we'll start up with law of mass action. I hope everybody is able to understand now what exactly do we mean by equilibrium and all those stuff, right? Very, very important, right? Any questions anybody has? Okay, fine. Thank you so much. We will meet again, I think by tomorrow or by next week. Thank you so much.